chaos. Now, before I go any further, let me just write down the credits. What I'm going to talk about is joint work with Grigory Verkholayko. Yesterday. And this paper is about to appear in Transactions of the AMS. In fact, I checked last night. It's appeared under the recently posted articles section. Oh, get off. Sorry.
Okay. It has appeared under the recently posted articles section of the Transactions website, so you can even download it without logging in. Okay. So I am going to start by giving some motivation for the problem, and this necessarily means that I'm going to repeat a few things that Uzi already mentioned in his lecture this morning, so I apologize for that, but I think it helps just to fix all of the ideas in everyone's mind freshly. So let me start with some motivation. And as with many talks already at this conference, the motivation will be a two-dimensional problem. So let X be a compact two-dimensional Riemannian manifold with negative curvature. So for people who know the subject of quantum chaos, this is a standard model. For those who don't, let me just say that this is a particularly interesting model, both mathematically and physically, because the geodesic flow on this surface is extremely strongly chaotic. And the point of quantum chaos is to understand the effect that chaotic classical motion has on the corresponding quantum mechanics. And for this particular model, the corresponding quantum mechanics are the spectral data for the Laplace-Beltrami operator on the same manifold X. So one will be interested in looking at the Schrödinger equation, which in this case is this equation triangle is the Laplace-Beltrami operator. And I incorporate all physical parameters like h bar and mass into the definition of lambda, which won't affect anything because I'm going to unfold the spectrum anyway. In fact, let me do that immediately. So since X was compact, then I know that there's a very nice spectrum with infinite many points, which I can order in non-increasing order. And actually, I will not use the raw spectral data as Uzi was doing in his talk. I will unfold the data so that on average, in any large interval of length L, let's say, there are about L of those unfolded points. This allows us to compare the data from different situations. Now, the effect of the very strong classical chaotic behavior on these eigenvalues is that correlations appear when you look at this set of points. And we have got very precise conjectures about what kind of correlations one will get. So let me write down something precise. So this conjecture, and the conjecture goes back to the early 1980s, the work of Bohiga, Strinoni, and Schmidt. And it concerns the nearest neighbor spacing density, which was already met. So I will write it in a slightly different form to Uzi's, but it's basically the same thing. So for two constants A and B, I'm going to count the number of points up to some capital N, such that the difference between lambda n plus 1 and lambda n lies between A and B, and normalize that by the number of points I could consider and send capital N to infinity. Then the conjecture is that this limit exists and is equal to the integral from a to b of a particular function p of s, where we have got a precise form for what p of s should look like. In common with Uzi, I'm not going to write down the exact formula for p of s because that formula gives almost no useful information. Instead, I'll write down the approximate formula, which gives all of the relevant picture of what this thing looks like. It's approximately pi of s over 2e to the minus pi s squared over 4. And this tells us that the spectrum is correlated, because if it would be uncorrelated, we would expect to get a completely different density here. So for uncorrelated, p of s would just be the exponential density of Poisson events. And the p of s that does appear in this conjecture is, as was described this morning, precisely the same density as you would get by looking at large random Hermitian matrices and corresponding and looking at the nearest neighbor of eigenvalue separation of those matrices in the limit that the size of the matrix goes to infinity. So that's where this p of s comes from. And one believes that, and I have not put a very important point here, if x satisfies a genericity assumption, it's believed that for any generic chaotic system, if one quantizes it, taking into account certain symmetries like time reversal symmetry, that one should get the same, for example, spacing distribution between nearest neighbor points in the spectrum, or other statistics too, such as the form factor, which appeared this morning, or instead of the nearest neighbor spacing, I could equally well look at the next to nearest neighbor spacing, or the distance between lambda n and lambda n plus r, which will be the rth nearest neighbor spacing, and I would just change here in this definition this 1 to an r, and then of course this density would change, but also it should be given by the same density for the corresponding problem from random matrix theory. So this is what's believed to be true for a generic chaotic system in terms of the eigenvalue problem. And these random matrix statistics are universal in that sense. So it should not really matter too much what the dynamical system was that you started out with. For example, here it was geodesic flow on some manifold, but the same thing happens if you take a chaotic map, for example, and you quantize the map and look at the eigenvalues there. Again, satisfying genericity, which means that certain nice maps like the cat map are not included because they've got arithmetical structure that renders them non-generic, or indeed quantum graphs, and I'll come back onto that in a moment. For the eigenfunctions, now going back to my manifold, we can say a little bit more. We don't just have conjectures, we have at least theorems in this case. So let me state a theorem. And this theorem is due to Schneelmann, Zeldich, and Colin de Verdier. So let f be a function on x. Chalk is a little bit squeaky. F be a function on x that's average value is 0. So if I integrate it over the function, I get 0. Then I take the eigenfunctions corresponding to the eigenvalues that I already talked about, particularly the nth eigenfunction squared, and multiply it against this function f as an observable, and integrate that over x. And I'm going to look at the variance of this quantity, so I'll square it. I'm going to have to erase that word. And sum over the first n eigenvalues, then this variance in the limit n goes to infinity is 0. And if I had not made this assumption about f, I could just subtract off the mean value of f inside this bracket. So the only effect of this putting f having mean 0 was that I don't have to subtract something inside here. So this is called quantum ergodicity. Because, for one thing, in the proof of this result, in fact, the only property of the dynamics that is used is just the ergodicity of it. Of course, in this situation, there are much more strong chaotic behaviors in the dynamics, but actually all that is used is the ergodicity. And the usual way that this result is stated, and a consequence of this vanishing of the second moment here, is that there exists a subsequence of eigenfunctions of density 1, which means that almost all of the eigenfunctions are included in this subsequence, such that along that subsequence, this integral inside here converges to the mean value of f. So it says more or less that almost all of the eigenfunctions equidistribute. But I've written the quantum ergodicity statement in this way, which is maybe slightly unusual, because it makes it easier to talk about graph problems later on. For the experts, of course, they will recognize that what I've written here is not really the true story. At least it's only a very small subset of what is true. Rather than considering functions on x, I could consider more general pseudo-differential operators, which correspond to an equidistribution not just on the surface of the manifold itself, but in the phase space corresponding to this problem. But that's a more technical statement to write down, involving quantization and things that I didn't want to get into. But I think that this statement that is written there gives at least a feeling for the thing that is true. So these are two typical behaviors associated to generic chaotic systems, and in this case, well, not much is proved. There are some sort of tools and some ideas about how one might construct a proof, but there are a lot of steps that are really missing. And so it was something of a breakthrough when it was realized in the early 1990s by Kotos and Smilansky that quantum graphs satisfying certain assumptions, which I'll get into, also appear to have the same random matrix statistics that are occurring for this more typical systems. And because quantum graphs are sort of mathematically more simple model than this manifold, it led to the belief, and indeed something which turned out to be true, that one could try to understand much better why these random matrix statistics are occurring and try to give proofs of them in the quantum graphs case. As far as quantum ergodicity goes, this is proved in most of the situations that I mentioned earlier, but still not proved for quantum graphs. And this is more of a puzzle than anything else. I mean, it should be also possible to prove it on quantum graphs too, and a lot of steps have been taken in this direction, but there are still some small parts that remain to be filled in my opinion. So the main point of my talk will be to discuss a result which we hope will be useful in the effort to try to understand universality of spectral behavior on quantum graphs. Now, there's one subtle issue, which I promised I would come back to. Let me do that now. And the subtle issue is this. If one takes a compact quantum graph, finite with finitely many bonds all having finite lengths, and looks at the spectrum of the Laplacian on that graph, of course one can do that. You get infinitely many points, and you could say, well, we try to do this kind of thing on that graph. And if you do the numerics very carefully, you'll notice that there are some persistent deviations from random matrix theory. And also, if you try to prove quantum ergodicity, it will turn out not to be possible because there'll be just some small persistent deviations from quantum ergodic behavior. And this is because each fixed graph has certain system-specific properties that cannot be washed away by looking higher and higher up in the spectrum. So it turns out that the correct thing to do, or it seems that the correct thing to do in order to resolve this, is to not just look at a single quantum graph, but to take a sequence of graphs, and along the sequence of graphs, they should have increasing numbers of bonds, and perhaps other conditions too, but certainly increasing number of bonds, and one might hope to recover things like quantum ergodicity or these random matrix spectral spacings in the limit as you pass along the subsequence. Now this introduces a little bit more complications into some of the definitions, but it seems that it's necessary to do that. So we have to consider not just a fixed graph, but if we want to make any hope and hope of getting proofs of these things, go along a sequence of graphs. Okay, so now let me talk about quantum graphs. Now I figure I don't need to write down too many definitions at this point in the conference, so I will consider a quantum graph with B bonds, or edges. That means there are two B directed bonds or edges, just giving each edge two directions. And a vector of bond lengths L and so there is a one-dimensional Laplace operator on each bond. What else? Plus some boundary conditions, and I will, let's say I use Neumann boundary conditions. I understand there is controversy about that name, but that was the name that I first started using, so I tend to automatically go to that name. And so for each graph, there is a spectrum. If I take the square roots here, I get a spectrum of points. I'll call lambda n. And the spectrum satisfies the Weyl asymptotic. Let me write that down as well. Actually, I will write down a slightly more precise version of the Weyl asymptotic. So it's curly L over pi. Curly L, and let me put that up here as well. Curly L, it's the same notation as this morning. It's the total volume of the graph, so the sum of all of the bond lengths. So this is proportional to capital lambda, and the error is big O of 1. Actually, I don't need such a precise asymptotic, but I learned a very slick proof of this, this asymptotic from a small paper of Daniel Grieser, and I like that very much. So this is a spectrum. As I say, we have got this subtle issue of having to pass along a sequence of graphs, but we could think about doing this kind of spectral statistics on this spectrum and see what we get. However, as the theory progressed, there arose another kind of concept of the spectrum for quantum graph, which started to get used a lot for some reasons which I will explain, which is slightly different from this notion of the spectrum. Actually, it looks completely different the first time you see it. It's slightly different from this notion. So let me explain what that is. I think I can erase the motivation now So this notion of a spectrum is actually already appeared in earlier talks. Sheet. So if one wants to find, let's go back to this spectrum. If one wants to find these values, of course it's straightforward to do so because this is just a one-dimensional differential equation that can be integrated in terms of a couple of constants of integration. We have got enough boundary conditions to be able to solve that system of equations that arises, and you get led to a condition for lambda to belong to this spectrum. Let me write down what that condition looks like. So by solving, in fact directly solving, we get to the following equation: z of lambda is the determinant of I minus s of lambda equal to 0. Right. I here is 2b by 2b identity matrix. S of lambda is a 2b by 2b unitary matrix. And in Rami Van's talk, he gave a nice exploded view of what this matrix actually looks like. So S of lambda can be written as a product e to the I lambda L. I'll explain my notation. E to the I lambda L times another matrix S0. E to the I lambda L is the diagonal matrix with phases that are proportional to the bond lengths. So e to the I lambda L1 right, and I assume that I've labeled the directed edges according to the convention that the second set of edges are exactly the reversals of the first set of edges. And S0 is a unitary matrix of size 2b by 2b, which gives the scattering amplitudes from one directed bond to another directed bond at a vertex. So this has already appeared in some talks. And no, they're both pluses. Perhaps my conventions are a little bit different to yours. And the important thing as far as we're concerned is that S of 0, because of the particular choice of boundary conditions we're using, does not depend on lambda. So that will be actually a little bit crucial in what follows. But as I say, at some point along the story, after the realization that quantum graphs had these random matrix spectral statistics apparently, people started looking at, rather than this spectrum, the spectrum of S for some lambda, or averaged over a range of values of lambda. So this leads now to a second notion of the spectrum, and at this point let me divide a board into two so that I can write down relevant things corresponding to two different kinds of spectrum. So we have got the quantum graph spectrum of this differential operator. You just write that. And then we've got spectrum of S of lambda, and so first of all, S is a unitary matrix. One sees quite clearly it's just a product of two obviously unitary matrices. So the eigenvalues of S are actually all living on the unit circle. So rather than looking at points on the unit circle, I'll just take the angles around the unit circle so that I get 2b. Let me check my notation using j here. So I get 2b eigenangles for every lambda. And in our paper, we called these by the names lambda spectrum and theta spectrum, just because it was easier to give them names that we could refer to them. Those names look a little bit silly now that I see them written on a board, but I believe it was my choice of name in the first place. Anyway, so we have the graph spectrum, the lambda spectrum, we have the spectrum of S of lambda, the theta spectrum, and we can also associate eigenvectors, or eigenfunctions, we should say. So for each point in the spectrum here, we have an eigenfunction which I'll denote by a psi. Right, and this actually belongs to some L2 space on the graph. And for each lambda and each j, there is an eigenfunction u j of lambda, which just belongs to a vector space dimension 2b. And quite a lot of the attacks on the problem of proving spectral statistics, or trying to go towards proof of spectral statistics having random matrix type, focused on this definition of the spectrum. It was always suspected that there was some connection between the two, and that at least the problems would be equally hard, and there are heuristic arguments given for why these things were the same. And the purpose of our work was to put a concrete foundation behind this, the belief that the two kinds of statistic are the same. Before I go into our results, maybe I give one or two or three reasons why this might be considered a slightly more attackable problem than this one, although these reasons are fairly subjective. So, first of all, of course, here one is looking at finite dimensional linear algebra. Whereas here we've got infinite dimensional problems. So from the point of view of the tools that one might use, it seems like this should be slightly easier. A second reason, which is maybe more relevant, is that we know that random matrix theory gives universal statistics as well. And what do I mean by that? Well, of course, these distribution functions that were mentioned this morning, that I mentioned slightly earlier, that come from looking at the neighbor spacing distribution of large Hermitian matrices. One could also think about looking at random unitary matrices. In fact, this is maybe even a more natural problem, because there is a nice compact measure on that set, and looking at distribution of spacings of angles of random unitary matrices. And taking into account symmetries, you find that you get exactly the same statistic for that case as well as the random Hermitian case. So if you want to prove that a certain thing has got statistics that are like random matrices, or random unitary matrices, and you have got a way of thinking of that thing as a large unitary matrix, remember B is going to infinity, then maybe that's a good way to start. So that's another reason why this might be considered a more attackable way to start the problem. And one more reason is that one can average over the value of the parameter that comes along here, lambda. And experience seems to have taught us that whenever you can average over something in these kinds of problems, you should do so, because this often gives a tool that allows you to make progress. And indeed, in certain works, this kind of averaging has been a crucial first step to get going. Okay. So now let me state our results. Let's do it down here. So I'm going to define the nearest neighbor spacing density for these two different kinds of spectrum. I have enough space there, so theorem 1. Right, so this is Berkeleiko and myself. So let H be a bounded continuous test function on the real line. Now I can define the nearest neighbor spacing density integrated against H. So we're on the lambda spectrum here. So P lambda H will be the limit n goes to infinity 1 over n. So n equals 1 to n H of curly L over pi lambda n plus 1 minus lambda n. This curly L over pi here is the factor that unfolds the levels to have the same, mean spacing 1. And the corresponding thing for the theta spectrum, p theta of H, limit as capital lambda goes to infinity. So there's going to be an average over the parameter lambda, and then 1 over 2b, some j from 1 to 2b, also averaging over all of the angles. This is never going to fit on b over pi theta j plus 1 of lambda minus theta j of lambda d lambda. So back to my theorem. If the components of the vector of bond lengths L are linearly independent over Q. So this is the standard assumption that the bond lengths are not rationally related. Then P lambda of H and P theta of H exist and define bounded linear functionals. Okay, and the interesting part, if delta L, which is going to be the difference between the largest bond and the smallest bond, goes to 0, then they coincide. Right, so the limit delta L goes to 0, P lambda of H, the same thing as the limit delta L goes to 0 of P theta of H. So provide I'll 1 minute. At the moment I don't assume B tends to infinity. So this just says for any fixed graph, in fact, provided one passes along a sequence of graphs with the same graph, but the bond lengths shrinking towards some common value, always holding this condition true, then the two notions of the nearest neighbor spacing density coincide. As John points out, I talked earlier about taking a sequence of graphs with B going to infinity, and it seems worthwhile to do that at the same time as you take the limit delta L going to 0. And then there is the question of order of limits, and it turns out that one can do it if B goes to infinity, then the appropriate rate of convergence should ensure that B delta L goes to 0. So B can go to infinity, but delta L must go to 0 faster. And it's notable that this condition, B delta L goes to 0, was speculated to be the correct rate of convergence well before we did this work. So this kind of justifies that that rate seems to be the right one. The method of proof, about which I will not say too much, does not change hardly at all if we consider, instead of the nearest neighbor spacing density, the rth nearest neighbor spacing density for any fixed r. So I could replace this n plus 1 here by n plus r and j plus 1 by j plus r. So in fact, it doesn't just work for nearest neighbor spacing densities, but all of the different neighboring spacing densities. And finally, I will say something about eigenvector statistics. And I believe I have just about enough time to do that. So for the eigenvector statistics, I just need to define a couple more things. So theorem 2, the same authors as the previous theorem. Same condition of irrational bond lengths. So I need to take an observable. I'll call this capital F. So it will be just a 2b by 2b diagonal matrix. And let me define a couple of quantities. So corresponding to integrating, if you like, the eigenfunctions against this observable f, let me define sin f sin n as the sum over the bonds b times the integral of the eigenfunction along that bond, and the corresponding thing for the theta spectrum, well, I can just look at f hat j, which depends on lambda and is just the inner product of the eigenvectors with this observable. So u j of lambda bar transpose f u j of lambda. Then what we could do was prove that m be a greater than 0 integer. The limit as n goes to infinity, L bar over n, sum n equals 1 to capital N psi n f psi n, the thing that was just described to the mth power, divided by that quantity, and that's equal to the limit as capital lambda goes to infinity, 1 over capital lambda, integral from 0 to capital lambda of 1 over 2b sum j from 1 to 2b f hat j of lambda to the power m d lambda. The things that I didn't define yet are L bar and the thing in the denominator there. L bar is just the mean bond length. Add them all up and divide by how many there are. And this quantity down here is the same thing that was defined here, where f is the observable that just observes how long each bond is. So fairly natural observable. And in fact, if you pass along this limit where delta L goes to 0 as before, then this number here approaches the mean bond length, and so those things cancel. And that shows that all moments of these two quantities coincide for the two different kinds of spectrum. Okay. I will not give proofs of this because time is short. Instead, I'll just whet your appetite by telling you what the ingredients of the proof are. So I'll write it here. The ingredients are, first of all, an estimate on the derivative of theta. So theta j of lambda primed it lies between L max and L min. The second ingredient is Weyl's law, which was already written on the board, and the final ingredient is also due to Weyl, the Weyl equidistribution of irrational flows in the torus, and that lies behind the assumption that was always there, that the vector of bond lengths are linearly independent over Q. So we have not done the more difficult problem of actually proving random matrix spectral statistics for any particular sequence of graphs, but what I believe we have done is by showing the equivalence of these two different kinds of spectrum given twice as many directions for attack at the problem, and that, I think, is our contribution to the subject for now. Okay, thank you very much.